Welcome everyone. This is a review for exam 2 in statics MET 111. We have chapter 4, which is we only need the equilibrium equations out of chapter 4, so they won't be exactly any problem asking literally like about the problems that we solved in chapter 4, but we need to know, for example, how to do a balance for a beam in order for us to do trusses and the bending and shear diagrams. So although the exam is only chapter 5 and the internal loading part, which is a separate chapter, but we still need to know the three equations of equilibrium, and that's why we need to know chapter 4. Okay, in this problem, we have this beam that under the action of two forces, the 500 pounds. It's kind of like it's not in the middle point, but they are equidistant from the two ends and from each other. And that should make the support forces at these 2 points equal. And that's probably what we'll be doing in order for us to find first the shear and bending moment diagram. So the first step is to find those two support forces. Here are A, so let's call this point A, and here B, and RB. And we only have forces in the Y direction, so I don't have any support or resistance I don't need the resistance in the X direction. So although it seems like it's a pin support, but we don't need to calculate the X direction because we don't have any forces that are inclined or acting in the X direction. All right, so we can take the moment for any point first, A or B, find one of the supports, and then use the summation of force in the Y. And that would be the 3 equilibrium equation. And why I'm saying 3, because we don't have X, therefore summation of force in the X, that's already satisfied. So the second equilibrium equation is take the moment, again, about any point you'd like. It's equal, let's take it about point B. So I have RA, it would be going in the clockwise direction, so 16 feet minus 16 times RA. And then I have 15 times 6, so that's 12. That leaves here 4 feet. So 10, and it would go, the first one, well, both of them, they would go in the counterclockwise direction about point B. So plus 15, 500 times 10, plus the other one, 500 times 6 equals to 0. And then we would solve for RA. We'll take it to the other side and then divide both sides by 16. That makes RA, if you notice here, let's take it first, 16 RA. What would happen if you factor out the 500? It's 510 plus 6, so times 16. Therefore, if you divide by 16, RA is equal to 500 pounds. Again, those two, as I've mentioned, since these two forces are equidistant, they will be equal and they would split whatever load you have. So it's just because it's 500, 500, that means it's symmetrical. And it's very similar as if we have 1,000 acting in the midpoint right here. So it would split between the two. All right, if we take the second, although we already mentioned RA equals to RB, but just to follow the procedure, I would have to use the third equilibrium equation in order for me to find the other support. So RA plus RB, both of these, we assume they're going up, minus 500, minus 500. RA is 500, so if we plug it, it would remove one and then take the other to the other side. Therefore, RB would be 500 pounds. Okay, so now I can start with the shear diagram. I'm going to start from the left and move towards the right side. So RA, it's going up 500, so I would go up 500. And then we'll keep moving until we hit the first critical point, which is actually, if you want to say that's the first, the second one is the 500. So I would keep going all the way till I hit that point, 6 feet. So we have minus 500, or because we're moving down, this is moving up. Then we move down 500, so I'm going to go back to the 0. That's the shear diagram here. We're plotting. And then we keep it's constant until we hit the second point, which is right here. And then we would move down another 500. So I would move down 500, and then we'll keep going until we hit the second support. It's 500 up, and that closes my shear diagram. Okay, so here we have 500. Here it's going to be 0, the value. And here it's minus 500. Why I need that? Because I'm going to use it for the moment diagram, and the value of the shear, we said it would be the slope for my shear diagram. Okay. So we plot this. That. Now, how many critical points? I have A and B. I need to know the moments at those 2 points. And then I have this point here and this point. So let's call this point C and this point D. All right, so the two ends, they have a moment equal to 0, simply because that's the condition for the beam to be balanced. So at any point when you consider the whole beam, all the forces acting on the beam, so it would be equal to 0. Here it would also be equal to 0. That's one explanation. The other one, if you want to use the left and right side, when we say, let's assume I'm going to take a section at point A, although it doesn't make sense, but just for explanation, take a section at A and take the left side. There are no forces acting. Therefore, the moment for the 0 force is simply 0. And the same for point B. Take a section at B and look into the right side. So the moment at point B is 0 as well, because there are no forces to the right of that. So those 2 points always, unless if you have an applied moment, and we'll see that in one of the questions, and you should have seen it in the homework. So those 2 ends are always 0, unless if you have an applied moment at that point, it would make it jump or change. Sometimes it goes up, sometimes it goes down, depending on the value of the moment. Okay, so I need to find the moment at C and the moment at point D. Again, there are 2 different ways which we can solve to find those moments. Let's use the regular method. I'll only find C, and then the same would go for D because it's symmetrical. So I'm at C at this point. If we take a section at C, and I'm going to look from the left, so I have RA equals to 500. And then here I have the shear. I don't need the shear. I'm only interested in finding MC. And then I have the 500. It's not going to affect the moment because it's passing through C. However, it is going to affect my answers uh, if we take it, if we take the moment for the section at A, should I include this here? Or should I include the right side, or should I split it? So to avoid that confusion, just simply take the moment here at C. This is only for this section, equal to 0. Therefore, I have minus 500. This is 6 feet times 6. I'm taking it about this point. So both the V, the shear, and the 500 are going to disappear. And I have MC, it's going in the positive counterclock direction. Therefore, MC is, if we take this to the other side, so it would be 3,000 foot-pound. We can do the same for D here. So if you take the section, so all what you have is simply RB times 6, so 500 times 6. And then you have the moment here going in the negative, so it would also give you 3,000. This one is 500, that's the support. And then I have here 500 MD. And I have also the shear. Again, I'm not going to find, or we already found the shear graphically. So I don't need those values. I'm only interested in finding MD. So again, take the moment about point D. So it would have 500 times 6, and then this one is going in the minus. So minus MD equals 0. Therefore, MD is 3,000 foot-pound. Okay. If you want to use the slope method, so we will take from here to here, from A to point C. What's the slope? Let's erase this. I don't think I have an extra page for that one. But the slope here, it's, so section AC. Slope for AC, it's positive 500. And that's equal to y2 minus y1, x2 minus x1. What's the y when we do the bending moment? That's actually what we're trying to plot. And the y, it's the moment. So it's mc minus ma divided by xc minus xa. That's the 6 feet. We already said ma, that's the end. It's equal to 0. So if you plug here 0, this cancels out. Multiply both by 6. Therefore, MC is 3,000 foot-pound. Okay, this is in feet. The 500 is in pound. So we get here 3,000. That's point C. Next, we'll do the second one. So if you notice here, that's A, C, D, and B. So that's the second one, section CD, the slope for CD, the value for the shear, it's 0, and that's equal to, that's A, B, C, and D. It's MD, so Y2 minus Y1 divided by 4 feet, and it's equal to 0, therefore MD is simply equal to MC, and that's what we got here, 3,000 and 3,000. I don't need to continue because we already found all the critical points, but you can always check on this, but we will do it in the second question. We will solve more of that. So I would now come, this is linear since it's only 1 point force. So it's constant. The shear, as you can see, it's 500. And then here it would be linear relation. So y equals ax plus b. And here it's 0. That's the slope 0. That means it's horizontal. And here it's minus 500. As you can see, the slope is negative. You can check it if you want. There are a couple ways how to check on that. So the slope for the last one, CD, we're saying it's minus 500, and that's equal to y2 minus y1. So it's MB minus MD divided by the distance, which is 6 feet. Now, how do we check? You can check for if we get a 0 for MB, or we already know MB is 0, so you can, because it's one of the two ends, so we can put here 0 and solve for MD and see if it's going to match this value. Okay. And here we're going to have minus 3,000 equals MB 0 minus MD. Therefore, MD is 3,000. So that's what we got right here. So whether I take either way, 0, I'm going to find 3,000. Or if I plug here 3,000, I will get here a value of 0. So as you can see, it's moving down, and that's what a negative slope is. All right. So that's how my bending moment diagram looks like for that beam. All right, we'll do the same for this beam. This time, the difference, although we've changed the supports, the loads, but the main difference is we have an applied moment acting somewhere in the middle of the section of the beam. Okay, so similarly, we will find the two support forces. I'm gonna move this to here so that we can solve a little on the right side. Start with the moment. I'll take about one of the two supports. Again, those two are parallel, so it's equal to 0. It'll have RA, it would go in the positive, so 3RA, 1.25. So this is also 1 meter, 1 meter. So that's 3 meters all the way to this point. And clockwise, so it's positive 3RA. The second one, it's 8 kilonewton. Also, it would both eights here are going also in the clockwise. So one is 2, the other is 1. So 2 times 8 plus 8 times 1. Here it's, as mentioned before, doesn't make any difference. But usually I put the force times the distance inside, just in case you get used to it. If you say, oh, we don't have a 2 kilonewton force, no, it's 8 times 2, the distance. Now, that's not all what we have. That's all the forces or all the moments created by the forces that we see from the support and the applied force. But also we have this applied moment, which is in the negative direction. So it's minus 20 equals to 0. So 20, and here we have 24. So that's 44 divided by 60 and 8. Yeah, 24. 44 divided by 3. It's not 45. I'm like, it's 20 minus 24, so that would be minus 4 only. Therefore, RA is minus 4 divided by 3, or minus 1.33 kilonewton. Those surroundings are going to create some difference at the end when we try to close the shear diagram, because this should be 1.3333 or 1.334. Okay, so if you round it down to 1.33, when you do RA, make sure it closes to the exact decimal point. Otherwise, you're going to have that small difference, which is not a big deal. Okay, so summation of forces in the Y, that's the second equilibrium equation. If you notice here, we assumed RA is moving down due to that moment to resist the moment, but my assumption was incorrect. And that's why we got a negative, but that's fine. Just leave it and put the sign here. So minus RA moving down, minus 8, plus RD. Now, the moment, it's a moment. It's a moment that's acting on that beam. It doesn't have a force. It should only be included in the moment equation, not in the force equation. So that's all the forces that we have. Plug that RA, so it would be plus 1.33. Take all the numbers to the other side, so it would be 16 minus 1.33, or 14.67 kilonewton. Again, I'm skipping the steps. You can do it. We've done a couple of these. A lot, actually, not just a couple. All right, so now I'm good to start plotting the shear diagram. I will start here, A, B, C, and D. All right, let's start here at RA. Again, that's the shear diagram, so I only need the forces. The moment shouldn't do anything for us. So RA, it's moving down. So before you start moving down, but it's 1.33 in the negative of my assumed direction. So it should be up 1.33. And then I will continue straight until I hit the second critical point at point B. I will move down by 8. So that would be minus 6.67. And then continue straight till point C. Again, I skipped this because it doesn't create any shear. I will move down to another 8. So that would be minus, we do this, minus 14.67. And then to here, if you notice, that's RD 14.67, and it's moving up. So I will go up and close at this point. So that's this point, that's point D. And then it would just continue straight at 0. Okay, that's my shear diagram. All right, let's do the bending moment. All right, as we said, RA and the support here, it doesn't need to be the support. It's actually the two ends. But at this point, I don't have any more forces. That's the last critical point. I have nothing to the right of that. So it should be 0 here all the way to here. Okay. Again, if you take a section here and look to the left, there are no forces. So MD is 0 and all the way till the end of the beam. So that's MD. It's 0 here, and that's A. This is point B and point C. Let's call that one as point C prime, if you want. That's where we're applying that moment. Okay, so the two ends, again, I don't have any applied moment on the ends. So here it's 0, and here all the way to the right, it's 0. That's my bending moment diagram. So let's start from the left. Slope for AB. So section AB, the slope, it's the shear, it's plus 1.33. First, we already said MA is 0, so that's my starting point. Now, what's the slope from A to B? It's Y2 minus Y1, so MB minus MA divided by 1 meter, that's the X2 minus X1, XB minus XA, so it's 1 meter. MA is 0, so this goes away, therefore MB, the moment at point B, is 1.33 kilonewton meter. So let's say it's here, 1.33. The second one, slope for B, but I have C prime, so I have to take it from B to C prime. Although BC, it should be the same. But because now we have that jump, it's going to be kind of it's like this, but due to that jump, I'm gonna either be like this due to that moment, or it would look like this. Okay, but those two, they both have a value of minus 6.67. So how do we find that? We will, so BC, I can say it's BC prime. So without considering the moment that we have here, the 20 kilonewton, so it would give me, before applying that, so let's call it here, let's write it first. MC prime, that's M2 minus MB, divide by, what's the distance? 0.25. So this one is without the moment, which is 20 kilonewton meter included. So what's my slope equal to? Let's put it here. Minus 6.67. This is slope for MC prime. We already found MB 1.33, plug it here. So minus 6.67 into 0.25 plus MB, so plus 1.33 equals to MC prime without the, or before applying the moment. So if we plug that, I would get minus 0.33. Let me do it one more time. 1.33 minus 6.67 times 0.25. Yep, minus 0.3375. Kilonewton meter. This is to the left, just exactly to the left of C prime. Left, because we're coming from the left and heading to the right. All right, now with the 20 kilonewton meter included, so the same, the slope for MC prime minus 6.67 equals to MC prime, if you want to put a comma right here, this is comma left, so left side, right side, minus, now I'm including that 20 and it's going in the minus, in the clockwise, so it's minus 20 minus MB. Divide by the distance, 0.25. And then I can solve for the MC prime. So it's minus 6.67 into 0.25. And then take both of these to that side. 20 plus MB equals to MC prime R. It's the same value, minus 0.3375, but we will add 20 to it. And that's actually what happened. Before applying that moment, it was negative 0.33. And then we applied a 20 kilonewton, but it's in the negative, so it has to go and it has to move up. And that's what we would get here, a positive value, which is 19.66, almost. Gonna be more critical. Let's do it exactly. MB is 1.33. Again, that's slight rounding. So 19.6625. So this is more than enough. MC to the right. Okay, what do I mean to the left, to the right? So now here's point C. The first one was negative. I'm going to just, I'll put it here, but I write the number here, minus 0.3375. And then to the right, so that means with the left, this would go from here to here, and then from here to here. And then here, this one is 19.66. That's MC prime to the right. Okay, so I'll connect this to the moment that we will calculate for C. But what happens here, that's the jump. So it's just a vertical line. That's how we know if it's, as mentioned, the slope is the same, but I'm gonna either go like this, move down and then go, or I'll move up and go. How do we know? I need to calculate before and after that point. And that's what we got from calculating the slopes at C prime to the left and C prime to the right. All right, the last one I'm going to take now, C prime C. The slope is minus 6.67. It's the same as this one. Here, nothing is changing. And it's equal to MC, that's the Y2 minus MC prime to the right, because now I jumped from the left, I'm now at the right, divide by 0.75, if I'm not mistaken. Yeah, 0.75. That's the distance, or x2 minus x1. We got this 19.66. Multiply that, calculate for MC. I would get MC equal to 14.67. Yes, this is exactly as the shear value because the distance is 1. So when we take the slope, it should be that value. So let's put it here. 14.67. So it would go as a straight line. And then I don't need to calculate this. So I'll just, because I already know MD is 0. So I would move down. If we don't know it, then I would say CD. The slope for that is minus 14.67. That's the value of the shear for CD. And it's equal to MD. That's Y2 minus MC divide by the distance, which is 1. So if we plug this here, take it to the other side, therefore MD would be equal to 0. Okay, because this is minus, this minus, we take it to the other side, so it's minus 14.67 plus 14.67, so it would give me a 0 value. And this would be my shear diagram. Of course, if I have a ruler, it would look more professional, but that's more than enough. All right, the third problem. So those are the problems that they're more than enough to review the internal loading. We went over how to find the support, and then we went over how to draw the same when we have an applied load. So this summarizes everything that we discussed. And we also did the method of sections. That's if I ask you to only find the moment at one point. So it's much easier to only include the method of sections. So here we saw the method of sections and the slope method. So the next two questions, questions 3 and 4, we will do trusses. So first, in this question, we need to find the force in each member of this truss, which is equilateral. All sides are equal, so 2 meter, 2 meters each side. We have a load here applied, it's 70 kg. So that would create a weight. That's 70. It is critical. I do need to multiply by 9.81. You can't just leave it as 70 kg. When we did the equilibrium and we were solving pulleys, it was fine to leave this if we're trying to find the mass of this, and I give you the mass here, because the gravity is gonna drop from my equation. However, here I'm asking you to find the force. The force has to be in newtons. So I do need to convert that into newtons. And we need to determine if it's under tension or compression. Just as a reminder, this support has 2 RAX, and since it's moving down, so probably I need to move up, but let's just put it this way. I don't know if I'm going to be even calculating these. And then we have RC, that's a roller support, so it doesn't resist anything in the Y direction this time. So it only has a support force that's in the X direction. Okay, because it has to be normal to the surface. Now, where do we start? I will start with this one is 686.7 newtons. I will start with joint B. Since I need to solve for all, so I'm not going to take sections. The next question, we will review the method of sections. So here, joint B, because it has 1, 2 unknowns here. If I want to start with A, then I need to solve for the external supports, or I can move to C. Still, it has 1, 2, 3, so I need to solve for the external supports. Okay, what do we have at B? I have the 686.7 Newton. And then we have here, this is 2. And so I need to know the slopes. Should be the same, 2, 2 here. This is 1, 1. Okay, so if we look into this one, the Y is 1, and here it's 2. So 1, 2, and square root of oh no, the hypotenuse is 2. Okay. So I know this is 1 and this is 2. So this is 1 and 2. I need to find the x direction. So it's actually 1 plus x squared equal to 2 squared. The hypotenuse squared, therefore x is 4 minus 1 square root. So it's square root of 3. Okay, here it's the same. 1 square root of 3 and 2. Because these are this 2 meter, that's the hypotenuse. Okay. So I will have FAB. And then I have, sorry, FBC, and here FAB. I will take the components of each one. So I have FBC. I have the slopes here, so I don't need. So this one would be FBC. The x component is square root of 3 divided by 2. And FBC, the y component is 1 divided by 2. The second one is, let's pick orange. I have FAB, it's the same, 1 over 2. And then I have another one here. I'm going to put it here, but going in the negative. It's FAB. The x component of the slope is square root of 3 divided by 2. Right, you notice both of these are inclined, and that's why we will have components in each direction. 1, 2, and also we have BC, BC showing. So regardless which one you use first, you're going to see both of these showing up and the same equation. However, since my apply this number, it's only in the y, I only have BC and AB in the x, and because it's the same slope, we're going to end up with BC equals to minus FAB. When you consider the summation of forces equals to 0, so I will have minus square root of 3 over 2 FBC minus square root of 3 over 2 FAB, that's equal to 0. So if you multiply the whole thing by 2 over square root of 3, so I'll have FBC plus FAB equals 0. So multiply it by minus square root of 3 over 2. Therefore, FAB is equal to negative FBC. So as you can see, we didn't really solve, and that's what's expected. We're going to have two equations, two unknowns, and that's one equation, although, but I don't have to solve that system of unknown. I can directly use the elimination method, and that's what we mean by the eliminate or the substitution method. We will take this and substitute it in the y equation. So here we have minus half FBC, and then minus half FAB. It's also moving down. However, FAB is minus FBC, and then minus 686.7 equals to 0. So here we will have something wrong. Just 1 minute. Oh, AB is moving up because that would actually minus half FBC minus plus FBC divided by 2. So it would cancel, and we're saying negative 686.7 equals 0. It doesn't make sense. Therefore, I knew something was wrong. This FAB is actually over 2. It was moving up, and that has to be plus half FAB. FAB is negative FBC. So from here, I will have minus half FBC minus half FBC. So it's minus FBC minus 686. I'll take it to the other side, 0.7. Therefore, FBC is minus 686.7. Therefore, it's under compression, and that's in newtons. Okay, therefore, FAB is also the same value. However, it's minus that, so it's minus 686.7 Newton. Therefore, it's 686.7 Newton, but it's under tension. Okay. I'm gonna move to point C. I don't calculate for RC yet. Sometimes I don't need that, so let's see first. If we need it, then we're gonna have to take the moment for the whole body. We'll take it about point A and solve for RCXY, because I only need to use joint C to find FBC and FAC. We already found FBC, so I'm only looking for this one, which is in the Y. Now, if you analyze it a little, I think we don't need RC because This is in the Y, FAC, RCX, it's in the X. So I don't need to consider the X direction because I'm only interested in knowing FAC. Let's look into the that joint C. I have here FBC. Again, we already have the slope. It's 1, square root of 3, and 2. I have RCX. And here I have FAC. I already found FBC. It's minus 686.7. So now if we decompose this, I'm looking for FAC. I didn't ask you to solve for the support forces. So this would be FBC square root of 3 divided by 2. That's the X. And the Y is FBC 1 over 2. I already have FBC. Therefore, if you look into the Y direction, I can find FAC because that's the only unknown. So don't solve. Actually, we can use this joint to solve for RCX without looking into the external moment equation for the whole body. So if you take now summation force in the Y equals 0, I have FAC moving up plus have FBC is equal to 0. Therefore, FAC is minus half FBC. So that's the minus minus. So it's 686.7 divided by 2, and that's equal to 343. Newton, and it's under tension. Okay. All right, the last problem, question 4, we need to find the force and members CD, which is here. Oh, that's too thick. Yeah, it was CD, HI, and CJ here. I need to find the forces. I'm not going to use the method of joints here. You can see how many joints. That's actually kind of like your project, except the supports are a little different. But if you're going to use the method of joints, you have to do each and every one of these to find the forces on these members. We have here all these forces given at each one. So remember, I can't cut, if I'm going to use the method of section, I can't cut through more than 3 members. So I can't cut like this, 1, 2, 3, 4. This doesn't work. I can't cut to cover all. Well, this doesn't make sense. Like, why did I decide to go that way in the first place? I might cut this way, so 1, 2, 3, but I didn't cut through that one. I can cut through 1, 2, 3. I don't know how to go to combine. Yeah, I can't have one cut that crosses all, even if it's gonna be 4. But just as an example. So what's the plan here? How do we solve this? I can cut through this, solve for HI, solve for CD and HC, and then use the method of joints, but only for one joint, which is joint C here, to solve for CJ. Or I can move from here to here, like solve joint. Since I already got HI from the section, I can solve for I to solve for IJ, and then solve for this. At this, well, we can't, I believe. Yeah, I can't take J because I need 1, 2, 3, 4. I have four unknowns in that case. So we can't do that. So never mind. Before we start, do you see any zero force member? Yes, I do. It's going to help us actually. And that's when we consider joint C is going to be very helpful because I have CD. I'm trying to solve CJ. So I already should have solved this one with the method of section, but I have one, two unknowns. But if you can't see any zero force member, now all these BJ, CI, and so on, you can't decide because we have uh, this force going down. So if you consider, for example, joint B or D takes summation of force in the Y, so I'm going to have FBJ equals to 1500. If I consider that's joint B, if I consider joint D takes summation of force in the Y, right here I have FDH equals to 1500 and so on. So these are not zeros. We do the same, except when we don't have a force, that would remove actually that member. So if you look here at joint I, take summation of force in the Y equals 0. What do I have? I have nothing, and I have FCI. That's it. I have the force going down here. That's equal to 0. Now let's take the section. Let's follow this line. And I don't want to solve for the support forces. So I'm gonna take the right side of the right section. So that's H, G. I will move down D, E. I'll connect these. Then F. First, let's put the external forces. I have here 1, 2, 3. All these are 1500. Here we have 3 feet, 3 feet. The vertical distance from top to bottom, it's 4 feet. Okay. Now, HI, FHI, and then FCH, and then FCD. Those are the three forces that I'm going to get when I make the cut. And that's my right side section. Before we start solving that, I need to know the slope for CH because I'm going to need to decompose this one. Again, if we didn't need CJ, probably I don't need to solve for CH if it was something else. So the slope for that, the Y is 4 and the X is 3. So 3, 4, and 5. Therefore, I'm going to have a force here that goes in this direction. That's some of this from somewhere else. That's FCH. I'm saying why it's now thinner. Right. FCH times the X component, so 3 divided by 5. And then we have here FCH 4/5. Okay, we're good now. So I need to solve now these three forces, HI, CH, and CD. Again, why we need CH? Because I need to use joint C later. So we'll start with the equilibrium for this section. We will take the moment about the point uh, that has the highest number of unknowns, which is point H right there. So summation of moment about point H equals 0. So all these here, CH and HR are passing through that point. Actually, also this 1500, it's passing through it. So it's not going to create any moment. What do we have? I have FCD. We remove this distance. It's 4 feet. So FCD going in the clockwise. So it's minus 4 FCD. And then the 1500, those are vertical. So I should be looking into the perpendicular distance to that point, which is the horizontal forces. One will have 3 feet, the other will have 6 feet. So minus 1500 times 3 minus 1500. I could just simply say 3 plus 6 equals to 0. Therefore, if I take that, so it's 1500 times 9 divided by 4. That's FCD, and that's equal to minus 3375. And it's in pounds. Therefore, it's under compression. Next, we'll take summation of force in the y equals 0. So I have minus 4 over 5 FCH minus 1500. That's it. Equals 0. Therefore, FCH is 1500 minus 1500 into 5 over 4. Oh, I missed that. I have not just one. I have 1, 2, 3. We're doing summation force in the y, not a moment. So it's minus 1500 minus 1500 equals to 0. So I will need to multiply this by 3. Before I multiply by 5 over 4. So we'll take CH to that side. So this one is times 3 times 5 divided by 4. 5,625, and also it's under compression. Okay, and then we'll do the summation of forces in the x direction. Equals to 0. Therefore, I have minus 3 over 5 FCH. This one. So it's minus 5625. And then minus FHI minus FCD. All of them are going to the right, to the left. And then I can solve for FHI. So let's take it to that side. FHI, that's equal to here 3 times 5625 over 5. And then plus, minus FCD, but FCD is minus 3375. So it's plus 3375. Therefore, we can find FHI, and that's equal to 6 1,075 pounds, and since it's positive, therefore it's under tension. Okay. So now I got CH, I got CD. This one we said it's zero, so it simply goes away. So now I need to consider joint C. I have FCD, I have FC, CB or BC. I have the member that I'm looking for, CJ, and it has a slope of, we already found it, similar, 3, 4, 5, and I have FCH, and I'm gonna remove this one, we already said it's 0 here. FCH with a slope of 3, 4, 3, 4, 5. Okay, so I can have FCH 4 divided by 5, FCH 3 over 5, that's this one. And then the other one, I'm not done here yet. I do have to put the applied force because I have the 1500. Again, that's a very common mistake that students make. I have FCJ. Let's do some. Let's move this up. And then 3 over 5 and FCJ 4 divided by 5. Now I need to find CJ. Excuse me. I already solved for CH. And I have the 1500. So I can only consider, you don't need to look for the Y because we have FBC and CJ there. So you're going to have to start with the Y either way. But if you were asked to find FBC, but we don't need that, I'm trying to only solve for CJ. So we have 4 over 5 FCH plus 4 over 5 FCJ minus 1500 equals to 0. Therefore, FCJ plus FCH equal to 5 over 4. We take the 1500 to the other side, multiplied by 5 over 4. And then I wrote it twice. CH plus CJ or CJ plus CH. Therefore, FCJ, that's the one we're trying to solve for. 5 over 4 into 1500 minus FCH. What was FCH? We just found it. Minus 5,625. Therefore, it should give me 7,500. That's a positive, and then Over there, we're gonna get also a positive value. So it would be under tension. Okay, so that would be the solution for the problem they asked for. If you want to summarize here, CJ, I don't need HI and CD. CJ is 7,500 pounds and it's under tension. HI was 6,750 pounds. That's HI. Also, it's under tension. And the last one was CD, which we found it the first 13375 pounds, and it's under compression. Again, since I'm mentioning tension and compression, so I can drop the signs. And that's the advantage of assuming that all members are always under tension. So whatever answer you get at the end, the negatives are going to be compression, the positive value are going to be under tension. Okay, and this concludes this question. If you want to analyze it, you're welcome to, but some people, they try to analyze what's happening here to the sections. Both CJ and HI are under tension, so they're pulling on the joints, and the members are under tension. Whereas CD, let's check which one is CD here, it's under compression, kind of like the two forces are not only these two, but in general, you have couple, you have three here, you have two on the left, they're pulling down, so kind of it's gonna compress that, but it would elongate this and this one. And that's why we got HI and CJ under tension. Okay, thank you.